Okay, so today we're going to have a look at the next in the sequence on high efficiency transference of electric power. What I did last time was looked at the high efficiency in the close midfield region. That was with the transmitter and the receiver secondary coils spaced by about 2 meters with a single wire in between the bottom of the secondary for the transmitter and the receiver. And in those experiments, which is already posted on the site, we were able to get efficiencies over 99% and also passing more than 500 watts of power down a single wire of only a 40 AWG wire. So it's a 80 micron wire, 0.08 millimeters. So that was the first step in the sequence. What we're going to do now today is we're going to have a look at transference of electric power and the efficiency over a larger distance. So in this case, what I've done is I've separated the transmitter and the receiver coils. So here we're looking at the transmitter setup, and I've got this in the far corner of what I call the lab room here, and I've got the receiver, which I'm going to show you in just a moment. I've got that down in the other end of the workshop. Now, in these two rooms that we have here, this is the furthest distance that we can actually separate these two and keep them inside. There is actually a second lab which is in another building, and that's actually further distance still, so that will form another part, a subsequent part, when also we will be able to have a look not only by single wire between those two rooms, but also through a telluric connection as well, before we go out obviously into the far field for the study of telluric transference of electric power. So the single wire between the transmitter that we can see here and the receiver is 11 meters long. So we are doing transference of electric power over an 11 meter single wire, and that's AWG, a 12 gauge micro-stranded silicone coated wire. That's a normal type of wire that I use for the HF work. So the setup is much as we used before. I'm using the linear amplifier generator with the power amplifier, those again the Kenwood. I'm using the 85K Powerstar antenna tuner with the incoming SWR, MFJ FWR, as you can see in the picture. That is connected through a 4-to-1 balun on the output of the antenna tuner that's built in, so we run it in balanced mode. That is connected to the Bird through-line wattmeter, the 44108, that you can see in front of you. There was the same equipment that was used in the first part of this series. And then the output of that meter goes through and connects to the primary. So we measure the power actually going into the primary circuit for the transmitter. And then the single wire you can just see the single wire coming out. If I just zoom in a little bit, let's just do that. The single wire is there. It's coming down past the amplifier on the left before heading into the other room. Now also I'm going to be taking some Z11 measurements, so if I just pan around so you can see the rest of the setup. Okay, so there I've got the normal setup. You can see in the background next to the computer is the DG8 SAQ USB vector network analyzer that's used a lot on the site, connected to the computer, the VNWA software. And I'm also going to be taking measurements of how Z11 looks, whether or not we can see the receiver at this much more distant point, and overall how that looks in several different configurations. Okay, so before we go any further, I'm just going to show you the rest of the equipment setup. Okay, so I've detached the camera now from the tripod, so we can move around the lab. You can see this is the setup that we were looking at before. There's the transmitter, and the single wire you can see is coming out there, down onto the ground. That's a silicone coated 12 gauge microstranded wire. I use that a lot. I haven't made any consideration here about supporting it, it's just trailed on the floor, so just as it comes. It comes down here, and down the steps into the workshop, and heads off, down the workshop, and there's the receiver coil. So it's just trailing on the floor. We come down and we have a look at this now, and there it goes into the bottom end of the secondary coil. And we'll just have a look at this setup here. This is the receiver coil as it was before. We've got the power meter again on the output of the receiver primary circuit, the tuning, and we've got the 500 watt lamp load that's integrated together. There's the 100 watt 4 bulbs and the 500 watt of the single bulb in the centre. They can be connected in different configurations. In this experiment we're going to be using the 500 watt, and we're going to make a measure. Now what I can do is I'm going to set up this camera remotely to remote control view the power meter at this end whilst I'm adjusting the transmitter, and then I can actually see both of those at the same point, and we can see what kind of measurements we're actually getting. So this is the setup of the receiver, and in between there is just over 11 meters of single wire. So I'll come back down the lab. There's a single wire, goes up through. I've kept it away from large metal objects if I can, but you see there's plenty of metal machinery in the workshop, and it's just trailing past those things. Up into the lab, and then back round to the equipment, and that's the complete setup that we're going to use here for high efficiency transference of electric power experiments over 11 meter single wire, and without taking into account considerations such as the alignment of the coils. I've just aligned the coils at the furthest most part that I can get them in the lab and the workshop. So I've remounted the camera on the tripod and just going to make a few considerations about the experiment first of all. Now, in the close midfield region where we did the last set of experiments on or the first experiment in the sequence on high efficiency, we went for a very balanced condition. So in other words, the highest efficiency was accomplished by setting up the cavity so making sure that the matching was right between the linear amplifier and the primary, setting up the cavity so it was as reciprocal as possible, and we did that by balancing the parallel modes, so adjusting the capacitance on the primary tuning capacitor on the transmitter coil on the primary, and the primary tuning capacitor on the receiver. We balanced those until in the Z11 characteristics we got a nice even balance between the parallel modes, and that was a high Q situation. So when we set that up and then small adjustments and when we put the load on the end and readjusted to rebalance, then we were able to get the highest efficiency and the maximum power throughput from the linear amplifier through to the receiver, to the receiver coil, and obviously powering the incandescent lamp there at 500 watts or more. Now, initially we're going to set the experiment up here the same. It's more difficult to set the transmitter and receiver to a balance point because the receiver is further distant. So, in other words, the reflections now coming off of the receiver back through the transmitter into the measurement are smaller, and we're going to see how that actually has a look, how that looks when we measure it. Now, just also to say that setup, when we run it, doesn't actually lead to very good power transfer efficiency. Unlike the very close midfield region, we are still in the mid region, but somewhat further away. We actually have to specifically set the transmit and receive coils up differently, and I will go into more detail when we get there in order to get the efficiency up into the high efficiency region, so up at 75% and above, and into the 90% regime. So first of all, we're going to take some Z11 measurements, and I will move the recording to the computer so we can actually see what those Z11 measurements look like, and then we're going to actually take measurements transferring power from the transmitter to the receiver, and then reconfigure the system and take those measurements again.
Okay, so we've switched to looking at the Z11 measurements. The system is set up as I showed in the first of all in the video. So the transmitter and the receiver Tesla coils are connected by a single wire transmission medium, a single wire just over 11 meters long of 12 gauge micro stranded silicon coated wire to form a TNT system and a cavity between the two. That is the maximum distance I can get them apart in this in the lab here. One at the end of the workshop and one at the lab, and the single wire just runs on the floor between the two. So for this first set of measurements, I've disconnected the 500 watt incandescent bulb. So we're just going to look at the two Tesla coils connected together by the single wire, so in a high Q state. So let me start the sweep here. We are going between 100 kilohertz and 5 megahertz. It's a normal kind of band sweep that I do for this kinds of measurements. And we can see what typically I've shown for a TNT system of two connected together, the transmitter and receiver coils, in other posts on the website. So if we look at what the results we can see, so at marker 1 there, down at the bottom here, we have the series fundamental resonant point, the resonant mode. That's at, we could just put it at about a phase of, that'll do, about 1 degree. 2.02 megacycles at that point there. So that's the series fundamental resonant mode. And now we can see the parallel modes. We note from other measurements that the parallel modes are much closer together than they would otherwise be. So there are two parallel modes from the transmitter, one from the primary, one from the secondary, and 2 parallel modes from the receiver, one from the primary and one from the secondary. So that results in these four peaks. But we notice that of previous measurements where we're in the close midfield, so the coils maybe only be separated by the 2 transmitter and receiver, only separated by a single wire of say 2 meters. We can see that the coupling between them had a greater influence. So the parallel modes were more separated, and that's because there was a greater interaction between those modes when they're in closer proximity. But with the distance now, there is a lot less coupling between those. The interaction between them along the distant wire is less, and essentially because that coupling between those modes has gone down, so the gap between the parallel modes has also gone down. So we have a mode due to the transmitter and modes due to the receiver. We can see that there's a tiny phase change there, very small, and one on the other side as well. That overall represents a typical Z11 characteristic for a TNT system. But here, of course, with the receiver being more distant from the transmitter, so that interaction between the two has reduced, and in effect the transmitter has started, essentially, is heading towards just being its own, on its own. So that's also partly as a result of course, the amplitude of the signal that we're actually putting in to this. I mean, this is a small signal analysis. The input magnitude level at 0 dB, or 0 dBm. So that also then obviously has to see what's at the other end of the single wire at a distance, and get a reflection off of that. That reflection comes back along the single wires, transformed down through the transmitter, and then we see those parallel and serial modes reflected in the input impedance Z11. But because the receiver is more distant, those effects are very small. But nonetheless, the parallel modes are there strong. So suggesting, I have conjectured that those parallel modes contribute directly to the LMD mode in the cavity. They are part of the formation of that. So when you drive at the series mode here at marker 1, there is coupling within the Tesla coils between the modes, and you end up with pumping a Tesla coil in the transverse modes, in the TM mode, but you end up coupling energy in the coil into the LMD mode, which when you form a cavity with another reciprocal Tesla coil at the other end, that's where we can then start transferring electric power via that mode via single wire transmission medium. And then of course that's transformed at the other end back into the TM 2-wire circuit at the receiver where you would have a load. So, okay, so we're running this now continuously updating. I'm going to, first of all, I'm just going to pull out the single wire. So if I pull the single wire out completely, obviously the wire length has now changed, which is why this has now changed the position in frequency. So this phase change has changed. And of course we've got the 2 parallel modes. Again, not balanced, of course, because we've taken out the influence of the receiver. I can adjust the primary capacitance to balance those. I'd have to go up a scale here. Okay, let's go up there. We can see those peaks. So we could balance that. Now that's just the input impedance of the transmitter itself with no single wire. It doesn't even have a bottom end extension, which is why the frequency jumped up. If I But you notice there are only two parallel modes here. If I now plug the single wire back in, okay, I've plugged the single wire back in, we can see those phase changes have reoccurred, they have reappeared from that's the interaction between the transmitter and the receiver. Of course, we're unbalanced again. We can't see the parallel modes coming off of the receiver, but until we rebalance, bring back those parallel modes, very similar frequency, head through that balance mode, and their transmitter heads back out the other way. So here, the frequencies of the upper and lower parallel modes are very similar. That's why we see those peak splitting, two resonant circuits resonating at the same frequency, though they are distant to each other, so that's why the coupling is low. That's the same effect you would see if you had the resonant circuit of a transmitter and from the primary and the secondary, and you started to pull them apart, so the coupling coefficient K, the magnetic coupling coefficient K between the primary and the secondary starts to reduce, and we'd start to see those two parallel modes start to move towards each other, and eventually, when there is no coupling, just simply represent one peak coming from the primary when the secondary has moved out of range. So very, very similar effect here. We're able to adjust it quite well. A reasonably good balance. With I have spent a little time running backwards and forwards to the receiver, adjusting that to get around about the optimum point. Now this is close now to the optimum point. Drive frequency 2.02 megacycles. Phase change shows the fundamental resonant mode at marker 1. In the write-up, I'll put the other markers on here so we can see what the frequencies are. Actually, I'll add one so we get if I pull that down there, so the lower parallel modes are somewhere around about 1.73 megacycles. The upper parallel modes are around about 2.4 megacycles, as we can see here. Okay, good. So that's the balance situation. But what we're also going to find out is that the balance situation like this, when you connect a load, obviously it significantly unbalances. That, as we've seen previously in previous posts on driving large loads in transference of electric power. So I'm just going to do that now. I'm going to go and reconnect that, and we see how that changes. Okay, so I just went down to the receiver and I've reconnected the load. So let's continue the sweep. And we see what's happened here now. So we've connected the load. We effectively have, because of the heavy loading at the receiver, we've essentially suppressed the parallel modes. You can no longer see them. Let's adjust around. And we've balanced up the parallel modes. That's only the parallel modes from the transmitter. And here we have this peak corresponds to the impedance peak here. Let's have a little look at that. Okay, so the heavy resistive or low resistance of the 500 watt bulb plus its the inductive reactance of the filament has skewed the response here with that loading. It suppressed the parallel modes, or appeared to suppress the parallel modes in the receiver, and pushed slightly the series fundamental resonant frequency. Okay, so what I've done now is I've reconfigured the system. So the transmitter is now set to 4 turns. That's the full use of the primary that I've got there. And I've set the primary tuning capacitance to its maximum over 1200 puff. I have the exact value be on the write-up on the page. And the receiver I've reduced to 2 turns. So they were both on 3 turns before, transmitter and receiver. Now the transmitter's on 4, the receiver's on 2 turns, and the capacitance is reduced. The primary tuning capacitor in the receiver is reduced to around about 150 picofarad, that's the position I found the highest just through empirical experimentation. I found that I can get the highest transfer efficiencies. So let's just put that on scan and see what difference that makes. So if we now look at the operating frequencies, so I'm driving at 2.1, which is still, that hasn't changed a great deal, it's still in this region. Parallel mode, so the parallel modes now are very unbalanced. So this is for the, let's just pause that. This is for transmitter. We see it's essentially collapsed the upper parallel mode at the receiver end around the receiver. This phase change is emphasized, and the only dominant parallel mode now is that in the primary of the transmitter. The other parallel modes, they are here, but they are very, very significantly suppressed. Let's try going in here and having a look. There we are. We are driving at about that point there, at that peak. 2.01 is where I have found 2.01 megacycles. So in this region, I found the highest efficiency for transference of electric power. So what you could get out versus what you could put in. So, I mean, on the video, I was showing in the most optimum position, 400 watts in and about 380 out, which was an efficiency of 95%. That was reasonably consistent. It started to fall off as you went up to about 500 watts when the lamp was fully illuminated. Then we were sitting about 460. 460 divided by 500 is 92%. And then at the lower powers, so 300, 200, is very much consistent, somewhere between 90 and 95%, depending on how you detune the linear amplifier. I was doing points at pi over 2, 1.618, which was the golden ratio, and also up to 2.0 SWR detuning points, which also has an interesting impact on the efficiency. So let's just zoom this out again. So interestingly, this represents the optimum point that I found so far in this experiment at this distance. We'll just scan it again. This was, of course, with the 500 watt load connected. And strong emphasis of the transmitter parallel mode, with not strong emphasis on the receiver parallel mode. So that may be indicative. It might indicate the idea here is to set up a strong LMD mode from the transmitter end, which reaches out over to the secondary. We can transfer that power through the longitudinal magnetic and longitudinal dielectric fields. The LD modes form together into LMD. That may be why this configuration is better rather than the reciprocal balanced condition that we found when we in the close midfield region. Okay, good. There will be, I will put these Z11 scans into the write-up on the page, so and add markers to the various points for more detailed consideration and analysis there. But this is suffice to show that there is a very significant different setup conditions for this experiment than we've previously operated, but nonetheless we are able to facilitate high efficiency transference of electric power over 90% by this way. In the balance condition, as we'll show in the video, 35 to 45% is the maximum that can be achieved where the parallel modes are balanced between the transmitter and the receiver. So it seems that emphasizing the parallel mode in the transmitter here is preferable as the distances go up in a single wire. Great, okay, so that's this section. We're going to move on now to actually looking at the experiment with the linear amplifier.
Okay, so the system, transmitter and the receiver are now set in balanced mode. So in other words, they have the same reciprocal setup, and according to where on the Z11 you would balance the parallel modes. This was the same position which we ran the experiment for in the first part of high efficiency transference of electric power in the close midfield region. So those parallel modes are balanced as shown in the Z11 characteristics. We have 3 turns on the transmitter primary, the 3 outer turns, and the capacitor here is set at the right position to balance those parallel modes, as is the receiver. So there's a reciprocal setup. There's 3 turns on the primary of the receiver, and the capacitor is set closely in order to get that balance as we showed in the Z11. So I've set the remote camera on so it's recording, so we can see and I will show some of this footage on the final video. We can see the receiver power meter through the remote camera, so I can see how that directly, here's the remote camera and here's obviously the power meter for the transmitter, and I can compare the two. So first things first, we make sure the power's wound down, turn on the linear amplifier, no power coming out, or very, very little. I'm going to wind up first of all to get about 30 watts, and I'm going to need to make some adjustments here. Get the best tune position whilst we're at relatively low power, 1.5, 1.3, get the linear amplifier tuned. That's fine for the moment, 1.2. I'm going to come up to 200 watts. Tune again, that's it, right down to 1. Optimise this. Load output of the linear amplifier, and then we can have a look at the efficiency that we're getting. Okay, so alright, so let me set it first of all to 200. So 200 watts in, only 80 watts out. Very low efficiency. 80 divided by 200, only 40% efficiency. Going to go up in power, up to 300. In, get that close to 1 as possible. Adjust the drive here to optimise. So we're sitting at 330 in and 140 out. So still the efficiency is quite low. So 140 divided by 330, 42.4% efficiency. So with this reciprocal setup, the efficiency is actually quite low. We're not getting that much power out in comparison to what we're putting in at this particular configuration point. And this was the balanced configuration, but with the load at a distance over this longer single wire, that completely changes the operating characteristics, where we've got to set this system up to. Okay, so 1.07, so almost, let's bring it up to 400 watts. Slightly overdriving the amplifier. Just adjust this a little bit. Up to 500, but let's pull it back down to 400. In. So 400 in, 160 out. So efficiency drops right down. 160 divided by 400, 40% again. So at this setup, the configuration just doesn't lend itself to the establishing that LMD mode between the transmitter and receiver, with the cavity, the monopolar waveguide. We're just not getting the power through in those modes. So that means we're going to have to change this configuration. So we're going to imbalance the configuration, or if you like, set up a configuration in the transmitter and the receiver which is much more suited to high efficiency transference of electric power over a longer single wire. We're going to increase the coupling by increasing the number of turns, and also bringing a lot more capacitance in on the primary circuit to really pump the secondary hard at the transmitter end. And we're going to free up the receiver by reducing the number of turns by 1, so increasing it to 4 turns in the transmitter, receiving it to 2 turns in the receiver, and also loosen the capacitance considerably, just down to a few, between 100 and, let's say, 100 and 200 picofarads. And then we will take Z11 scans again, so we will see what that configuration, but that change of configuration, that somehow what's necessary to balance up the LMD mode over this long single wire is we're going to see our efficiency go up enormously. If we get it all tuned in the right place, everything, we should be able to get efficiency up over 90% by changing simply the configuration of the transmitter and the receiver setup. So that was the balanced situation. Works very well in close range on a short single wire, but even when we increase the single wire now from 2 meters to 11 meters, we've got to put a completely different setup on both the transmitter and the receiver coils, and also we'll also show the effect of selectively detuning the linear amplifier from the system at pi/2, the golden ratio, and up to 2 slightly above, and how that also impacts on the efficiency. Okay, so I'm going to reconfigure the system here. Let's just take another measurement, make sure we are done what we can. 400 watts in, 160 out. So it's been sitting there stably while I've been talking. 160 divided by 400, 40%. And if I just pan out, we just see what the bulb looks like at the other end. Yeah, so the bulb looks reflective of the fact that we are actually really only measuring about 160 watts of power. It's 1/3 of its maximum, just under 1/3 of its maximum illumination for 400 watts of power going into the primary circuit, and that was for the balance condition. Okay, I'm going to reconfigure, and then we come back and we start same measurements again, but then with a reconfigured transmitter and receiver. Okay, so we're viewing the remote camera here, which is zoomed in, looking at the meter of the power meter, so we can make some comparisons. I'm going to turn on the linear amplifier. It's wound down at the moment. I'm just going to bring it up to 100 watts to start with. We can make sure everything's tuned and adjusted correctly. So bringing it up to 100 watts, just on 100 in, and very close to 100 coming out too. So let me just adjust. Just let us tell you are, just for the moment, for a perfect match. Okay, so I'm going to bring it up further. Let's come up to 200. See how we're looking efficiency wise. Okay, so it's just on 200 going in, and 190. So 190 divided by 200 is 95%. So now on 200, so 210 here and 200 there. So 200 divided by 210, 95.2. 220, 210. So 210 divided by 220, so stably sitting around about 95% transference of electric power between the two at 200 watts. That's good. Let's bring up the drive a bit to 300. Okay, so we're rather overdriving the valves, so let's just wind them back down. Okay, that's better. Get it into a better position. So again, efficiency looks quite good. So 400 in, 380 out. So 380 divided by 400, 95%. So we are staying stably at 95%. Let's come up to fully illuminate. 500 watts in for, let's just adjust linear amp, it's driving a little bit hard. 500 watts in, 460 out. So 460 divided by 500, 92% efficiency. Let's just have a look at the illumination of the bulb. Come right out. All the way out. That bulb is lit brightly. So 500 in. Bright illumination. Driving the linear amplifier, a little bit over driving on the grid current to put this much power through. So let's go zoom back in again. Have a look at our results when we zoom. We're able to get it zoomed properly. Further. Rather far away for the remote control. The remote control gets a little bit, takes a little while to respond. Further we need to go. Is it better if I slide it? A bit more. Very good. I'm going to wind it down a little bit now because we're driving quite hard. Just bring it back to 400 in and make some comparisons. Okay, so just check tuning again. Get the linear amplifier happy. The amplifier really is sitting in its, not overdriving anymore. So we are putting 400 in. And we have got 360. So 360 divided by 400 is 90%. A little bit less efficient as we go down. See if I can adjust that. Drive the linear amp a little bit harder. 380 going in, 340. So 340 divided by 380, 89.4. Set optimally. So 410 and 370. 370 divided by 410, 90%. Let's go down a bit further. Let's go down to 300 watts. See how it looks there. Ooh. There, just adjust the linear amp a little, just over 300 watts. Okay, so 310 and 275 I would say. So 275 divided by 310, 88.7. $300, 270. 270 divided by 300, 90%. Just very small changes to the tuning make a difference. Let's try detuning now. So I'm going to take it up to 1.61. And now we have dropped to 230 and 210. So 210 divided by 230, 91.3. By detuning, I chose to detune to 1.61 SWR, which is fine, the golden ratio. And we are reading 230 to 210. That's 91%. If I detune further, So all the way up to 2. We are putting 190 in, and we've got 180 coming out. So 180 divided by 190, 94.7. So my efficiency here at lower powers is going up as a result of detuning. So deliberately choosing to detune the match between the linear amplifier and the primary of the transmitter is actually improving our transfer efficiency here. So stably on 190 and 180. So 180 divided by 190, 94.7%. Let's go up again and see how that detuning. Be careful not to overdrive the linear amplifier. In its detuned state. So 300 to 75, slightly more. 275 divided by 300, 91.6. So our detuning did, so now we're stably sitting on 300 in, 280 out. So 280 divided by 300, 93.3% at 300 watts going in. Okay, so the camera battery, the remote camera had actually, the battery had run out, so I've just changed the battery and we can go back. Everything remains the same. We just go back to where we were. Okay, we're at low power. Just going to run down just up to 100 watts, just make sure we're in the right regime. I'm just going to keep the match here to about 2. I don't want to overdrive the linear amplifier at the high powers with a large mismatch. So we're going to go back up. Let's check our measurement at 300. So 300 watts in, 285 out. So 285 divided by 300, 95%. Okay. And slightly better. We just adjust slightly. Optimise that, so keep that up at 2. So 305 in, 295 out. 295 divided by 305, 96.7. Alright, let's proceed up to 400 watts. Just going to adjust this so we don't overdrive. It's about 400 in. Just get 400, 400 in. We've got 385 out. 385 divided by 400, 96.2% at 400 watts in. 96.2% over 11 metre single wire. That's pretty good. The linear amplifier is not particularly overstressed. It is running fairly high. It's got its maximum grid current, which is around about 220 to 250 milliamps. We're just going to leave that now, and that's detuned at 2. So I'm going to retune it back, watching of course the drive doesn't get too high. Retune it back to 1, SWR of 1, so principle close to a perfect match, and see what that does to our efficiency. So far we would expect our efficiency to go down. in doing this. Okay, so now up at 500 watts in, so obviously with the match we can get more power in. Let's go back down to 400 so we can do a comparable result. Let's tune it onto 400. So at 400 we are on 360 out. So 360 divided by 400, 90%. So we have gone down in efficiency as a result of tuning. Changing the selective match between the linear amplifier and the primary circuit, and by deliberately detuning it we were able to increase that efficiency. So now let's go up to, let me have a look, so pi over 2, so pi over 2 at around about 1.57. It's about 1.57, and we are going to need to, I'm going to bring it up to the 400 watts again so we can do a comparable result. Linear amplifier good, 400 watts in, 360 out. So 360 divided by 400, 90%. So I'm going to proceed on to the golden ratio, 1.61. Adjust the drive slightly, optimise that drive. 400 watts in, 370, almost 370. Just slightly. 400. No. 360. So not a lot of difference at all. 360 divided by 400, 90%. So detune all the way up to 2. Bring up the drive a bit. Back to 400 again. Just on 400, and about 365. Slight increase efficiency. 365 divided by 400 is 91.3. Efficiency going up slightly. Let's see if we can tune that any better. Down to just to keep everything, just keep the linear amplifier happy. No, that reduced our efficiency. Then we just change the tuning slightly. Go back up to 400 with the drive. We seem to be sitting 400 in. Just under 360. So that seems to be about our optimum position. Tune it again. Adjust the drive slightly. Don't overdrive anything. 400 in, 350, 350 divided by 400, 87.5. Okay, so let's go down, back down to 200. do seem to get better efficiency in this region. So 180, 200 in, 180 out, 90%. $200, 180, all the same. Just change the tune again. So 220. Nope, that's made us worse. 250 to 220. 220 out, 250 in. 88. 225 to 250, 225 to 250, 90%. Okay, so I'm going to let the system cool down a little bit. So by adjusting and tuning at slightly different power points, we went from somewhere around about 90% up to a peak of just over 96% efficiency. Down 11 meters to single wire. And that was also made considerably different by the setting up the transmitter and the receiver according to the load at the other end in different scenarios. So in other words, the transmitter was set up so that it used maximum turns, more turns than you would otherwise use in the balance, close mid region. In other words, I'm using the maximum turns available for this primary. So in other words, maximising that coupling between the primary and the secondary. Combined with maximum capacitance. 1200, 1250 picofarads at the capacitance at the input to the primary, and at the receiver, the other situation. One less turn, so driving on 2 turns, and very low capacitance, about 100, 150 picofarad. And that seems to give us our optimal condition between the two. So what I'm going to do is I'm going to zoom out here, and we have a look also. I'm going to reposition the camera and set us to run at reasonable power, and then we will see. So I'm going to set us to run, turn on, at around about 300 watts. So we're not overdriving anything particularly. Actually almost 400. Why don't I set it run on 400 without overdriving the amplifier? Right, I'm just going to reposition the camera at the other end, so I'm going to turn off there. I'm going to go through and reposition the camera at the other end. So I've repositioned the camera so we can see the receiver. I'm going to turn on. Should be running up to about 400 watts. we can see the, yes, 400 watts, keeping a really good match. This end not overdriving the linear amplifier. That's it. Now I want to have a look at the tension at the other end. First of all, at the transmitter end, using a bulb, so we would expect there to be quite a lot of tension in here. The neon at the top end of the secondary there is very bright. Just obviously taking some power out there. Then I'm going to go through down to the receiver. So as you can see from at the receiver end with the fluorescent lamp, also a lot of tension on the coil there, and also considerable tension at the top end of the secondary, where we can see streamers. I could draw streamers off the end of the fluorescent lamp up to almost 1 inch long off the end. So there is a reasonable tension, considerable tension at the top end there. And if we consider what's actually happening here, so by setting up the transmitter and the receiver with 11 meters of single wire just laid on the floor as I showed, we are establishing what would look like the LMD mode between the transmitter and receiver in the cavity, and we were able to transfer, well, up to 96% we had at one adjustment, but reliably it would appear at many levels of tune, even when the linear amplifier is detuned up to 2 and at the golden ratio and at pi over 2, the mismatch, we are at about 90% high efficiency transference of electric power up to about 400 watts, and at maximum we had 500 watts. When you tune the linear amplifier for a good match down at 1, SWR of 1, then you're able to get 500 watts in and about 450 watts out at the other end. So the difference between the single wire before, when it was 2 meters and now 11 meters, and they are no longer in proximity to each other. So we're obviously still well within the wavelength. We're still in the midfield region. We're at the 160 meter amateur band. So we are, the single wire is still less than 1/10 of the transverse wavelength coming from the linear amplifier. We're able to transfer that much power at that much efficiency from one end of the single wire to the other, primarily from the LMD mode. So establishing that longitudinal mode in the cavity, remember that's both the magnetic and the dielectric fields of induction, and that is guided around the wire. So that is why we can transfer that power with relatively low losses, because it acts like a monopolar waveguide. In effect, we are guiding the LM and the LD modes from the transmitter to the receiver. And then, of course, through the receiver that couples with the series resonant mode, at that end, and is coupled into the primary. The primary, again, remember, is a 2-wire circuit. So we're going down from single wire transmission to dissipating power in a conventional 2-wire circuit in an incandescent lamp. Same in the primary circuit in the transmitter. We basically have the linear amplifier is basically driving a 2-wire circuit with a primary coil, and that is also why we are able to make power measurements. We're using the power meters within their operating band. Their normal band of operation is to measure RF power on a 2-wire circuit, and we're able to do that. That's different, of course, in the single wire. Measurement of power there, much more difficult to do, because we would need to know, we would take into account the configuration of the LMD mode and what a power measurement would mean in the single wire. That is a topic for another post, to look at power modes and energy conversion and transfer between modes, so between the transverse and the longitudinal mode, by virtue of the nature, the characteristics of the Tesla coil, that is those series resonant modes and those parallel modes interacting there. That is how we are able to do the kind of experiment that we are with Tesla coils. Great, okay, well, that is second part, high efficiency transference of electric power from, let's call it, say, between 90 and 95% over 11 meter single wire. Great.